All right, welcome class. We are in session 4. We'll review Ohm's law again, and then we'll look at series and parallel circuits. And again, the reason why we're reviewing Ohm's law is because when we look at series and parallel circuits, it's going to build off of that knowledge of Ohm's law. So let's look at the topics. Again, introduction to Ohm's law. We are also going to review the problem-solving method that we talked about in the lab, and also we will introduce series and parallel circuits. Our objectives are to identify Ohm's law and solve problems using it. Also to identify and describe series and parallel circuits, and also to use circuit equations to solve problems in series and parallel circuits. At the end of this session, we will be able to calculate, given a circuit, we'll be able to calculate the characteristics, whether it is a series circuit or parallel circuit. In the future, we're going to look at when we have series and parallel combined, how do we analyze that circuit? We also will utilize Ohm's law to solve problems, and also will identify and utilize some other laws. And these laws are Kirchhoff's current law and Kirchhoff's voltage law. Okay, so for review, I'm asking you to review chapter 3. Let's take a look at it. So again, here, this is a review of current, voltage, and resistance. I'm not going to go through it. It's for you to review. We also have the introduction of Ohm's law. Again, we have discussed this one. I'm not going to spend much time. It's for you to review. Here's a practical example of Ohm's law using voltage, current, and resistance. You can see here that we have a bulb that uses 120 volts, and the bulb is acting like a resistor, it's acting like a load, and then we are using the meter to measure the AC current that is going through the bulb. And so you can see that the meter is set to ampere, and again, it's reading 0.87 amps. And so if you were to find a resistance is going to be voltage divided by current, and we get a resistance of 158 ohms. So Ohm's law can apply to an entire circuit. It can apply to an individual resistor as well. Okay, we have another example here. Again, this is the results of where we have a circuit and we have a fixed resistor, and we simply increase the voltage here. So we increase the voltage and we measure the current. And you plot that on a graph, you will see that it is a straight line, and that indicates that there is the relationship between voltage and current is linear for a fixed resistor. Now, when you plot that, right, as you change the voltage, you measure the current. When you plot this line and you take the slope of this line, you're actually getting current divided by voltage, which is the same as conductance. And so if you wanted to find the resistance, you just take 1 over that conductance and you will get the resistance. Of course, if you plotted voltage here and current here, when you get the slope of this line, the slope would be the resistance. Some examples here. So what else do we have? Okay, you can see another example of Ohm's law here. Again, you can see how the breadboard is used, where the different rows are used to connect circuits, right? So to connect the wire to the resistor, you need to put it in the same row. So here we have a 15-volt battery or power supply, and it's going to a particular resistor. We are given the color code for the resistor, and using the color code, we can find what value the resistor is using the chart that we have. So green is going to be 5, blue, I believe, is going to be 6, and brown is going to be 1. So that would be 10. So it's going to be 560, and gold is 5%. And we're asking, what should the ammeter read? So again, if we have Ohm's law says that current is going to be voltage divided by resistance. So it's going to be 15 divided by 560. Let me just see if I'm right. Let's just check it quickly. 15 divided by 560. And you can see that the answer is 0.0267 amperes. And so if you convert that to milliamps, you move this up 3 places, 1, 2, 3, you're going to have 26.8 milliamps. Let's continue. Again, we have some questions about troubleshooting, right? Some of you build your circuit and the light doesn't come on, it doesn't work. So there's some questions that you can ask. Have the circuit ever worked? If it worked, under what conditions did it work? What are the symptoms of failure? What are the possible causes of failure? Right, so some steps to help you troubleshoot. Now, for the lab that we did with the light bulb, some of the steps that can be wrong or where you can go wrong is if you would not have your connections in the same row, then they will not be connected, your light will not come on. If the polarity of your LEDs change, where you don't have the positive 5 volts coming into the positive leg of the LED, then your light will not come on. So these are some tips to help you with your first circuit. Okay, so the rest of this is for you to review. Let's go on to the next, the remainder of session 4. All right, so we have 2 presentations here, one on series, one on parallel. So I'm going to leave these presentations for you to review. I also gave you some videos here on Ohm's law and some videos and series and parallel circuits that I want you to review as well. Let's see, have a look at this one. So like I said, if you have paper, you have your notebooks, please make some notes. This is very important. Yes, we have some slides that I will ask you to review because there's lots of information in there, but I'm just going to share it with you so that in a form that you can just take some notes. So I'll share my screen. Okay, can you still hear me?
Yes, sir.
Yes, sir.
Okay, great. So all the circuits we have looked at so far, they only have one load, right? Only one resistor. So how do we analyze a circuit with multiple resistors? Well, first we need to see, well, what are the different ways that we can have resistors? And so this is one load. So let's start with 2. If we wanted to have 2 resistors, there are 2 ways we can have these resistors. The first one is if we have our battery and we have one resistor here and we connect it like that, right? Remember, a circuit is an interconnection of circuit elements. So we have 2 resistors here. We can call this one R1 and R2. And this is VS. This is when we organize the resistors in that way, right? We call this a series circuit. Please make some notes. We say that the components are connected in series. And why is that? Because there is only one path for current to flow. If you look at it, if we say current is coming from our positive terminal here and it's going towards the negative, notice that the current has to pass through both of the resistors, right? So there is only one path for current to flow. Do you guys agree?
Yes, sir.
So this is an important feature of series circuit. Now, what that means is that it means that the current, since there is only one path for current to flow, if you measure the current here, we said the current is the rate at which electrons are flowing or charge is flowing per second, right? If you measure the current here, you're going to get the same current. If you measure it here, you're going to get the same current. If you measure it here, you're going to get the same current because there is only one path for current to flow. And so the current is the same everywhere in the circuit. That's another feature of series circuits. So current is the same anywhere in the circuit. Okay. The other thing we need to know about series circuits is that, remember what happened with when we did the experiment with the LED, right? We had 5 volts coming in, and then we had some voltage across the LED and some across the resistor, right? And when you added the 2 of these voltages, they added up to the supply voltage, correct? So the same thing happens with the resistors. Any voltage we have here is going to be dropped across the two resistors. So in other words, if you measure the voltage across this resistor and you measure the voltage across this resistor, it's going to add up to this one. In other words, this circuit is, if you simplify this circuit, you're going to get this circuit. And remember what happened. All the voltage of the power supply was across the load. But now, since we split the load in two, this is exactly what we're doing. Since we split the load in two, if you measure the voltage across this one and you add it to the voltage across this one, you're going to get your battery voltage. So we can say that the voltage drops across R1 and R2 is equal to RS, right? And that is what we call Kirchhoff voltage law. So KVL, and that says that VS is equal to VR1 plus VR2, right? That is Kirchhoff's voltage law. Again, we observed it yesterday. The sum of the voltages across the components in the circuit is going to be equal to the sum of the battery or whatever is supplying the voltage. Okay, so we looked at one path for current. The current is the same. We also looked at that the voltage drops is going to be equal to the voltage source. Also, the next thing we need to know is that if you look at here, we measured the total power that was consumed by the resistor. In this case, since we have two resistors, the total power that is converted by the circuit is going to be the sum of the power, right? The sum of the power used in each resistor. So we can say that PT is going to be equal to PR1 plus PR2. So the total power used by the circuit is going to be the power used in each resistor. Okay, what else do we need to know about this series circuit? Okay, we're going to pause right here, right? We're going to pause here about the series circuit. Let's talk about the parallel circuit. So again, if you have multiple loads, the other way you can organize the loads is you can either put them in series or you can put them in parallel. So what does the parallel one look like? Okay, it looks like this. Where you have one load here. So this is another way you can connect your loads, right? If you connect your loads this way, we say that they are in parallel. So this is called a parallel circuit. All right, so let's call this R1 and R2. Okay, the last thing, before we continue with this circuit, we need to talk about the total resistance. So again here, if you have one resistor, what is your total resistance? The total resistance is going to be the resistance of that resistor, correct? If you have two resistors, what is your total resistance for the series, let's see. What is the total resistance for the series circuit? The total resistance is going to be the sum of the two resistors. So if you add R1 and R2, you're going to get the total resistance. So RT, if we call this RT is going to be equal to, for the series circuit, R1 plus R2, because the current has to go through both of these resistors. So that's very important. RT is equal to R1 plus R2. All right, and of course we can see lots of examples. So again, these equations for each of these circuits we are going to use, so we need to be able to identify them. Okay, I think this is it. Let's come now to the parallel circuit, right? So notice what is happening here. The voltage is across R1 and the same voltage is also across R2, correct? So in the parallel circuit, we can say that the voltage across R1 is equal to the voltage across R2. That's the first observation we can make, right? We say that VR1 is equal to VR2 is equal to VS. So you can see that since they are connected, now again, keep in mind when we had one resistor, right? The voltage across the resistor was the same as the supply. What we are just doing, we're just adding another branch to this. We're adding another load. And so the voltage across it is the same. And this is the same way your circuits are connected in your home. For example, you have a panel, you have a panel with circuit breakers inside of it, correct? All of the circuit breakers are connected in parallel. That is why all our outlets have 120 volts, right? All the outlets have 120 volts because they are all connected in parallel. So and again, if you have a power strip, yes? If you have a power strip and you connect different items in your power strip, all of them get 120 volts, correct? So they are all in parallel. So just keep that in mind, right? Anytime something is in parallel, it's going to have the same voltage across it. The other thing we need to observe is that each resistor is going to draw its own amount of current based on Ohm's law. So in a parallel circuit, each resistor draws its own current based on Ohm's law. So let me make a note of that. Each resistor, make sure you take this down, draws its own current based on Ohm's law. Okay, what does that mean? Again, so a parallel circuit is very similar to the electricity circuits that we use in our home, right? So say you have a power strip. So this is your power strip here. And you're getting 120 volts from the wall, correct? Okay, so in terms of the amount of current that is so if you have a current ammeter here to measure current, right? If nothing is connected to your strip, guess what? No current is being used. If you plug your iron and your iron is drawing, say you have a 1,000 watt iron, and your iron is drawing X amount of amps, then of course the amount of current that you're going to use is going to increase, right? So let's put the iron is drawing 5 amps. And if you come in your strip and you plug your phone charger, and say your phone charger is drawing 0.5 amps, and then you come and you plug in your microwave, and this is drawing, say, 2 amps. Then you can ask, well, what is the total current that is being drawn by this? So all of these components, what is the total current they're drawing? To do that, you simply have to add the currents, right? You're going to have 5 plus 2 plus 0.5 amperes, which will give you 7.5 amperes. So the load, we call all of these loads, the load is going to draw a certain amount of current. And so that is why we stress safety when using like power strips. You are told not to overload them. What does that mean? It means not to plug too many loads that will draw too much current out from it. Most times the power strip is rated for maybe 14 amperes, or the breaker in your home is rated for 14 amperes. And if it goes over that amount of current, it's going to trip the breaker. So the more loads you add on here, the more loads you add, the more current is going to be drawn. And this is the same way it works in the parallel circuit here. So we have one load and we are drawing, say if we are drawing X amount of current if the load, right? If you add another load, you are drawing X amount of current again. So you can see that every load you add in parallel, the amount of current you draw from your battery is going to increase, right? So the amount of current, so again, we are saying each load draws its own current. So the total current is going to be the total current that's drawn by each load, right? So again, we have a amount of current going down here that is based only on this load, only on the resistance here. You have some current going here that is based only on the resistance here. Yes? And so if you ask what is the total current of the circuit, the total current is going to be the sum of each load, the current in each load. And this takes us to Kirchhoff's current law. We call it KCL. And what this says is that the current, now if you look here, we can see the direction of the current. The total current comes from the battery, and some of it goes through R1 and the rest goes through R2, right? And so you can see that they add up here again. They add up right here. So you can say that if you look at this as a node, you can say that the current entering the node is equal to the current leaving the node. So let me make a note of that. So current entering the node. And how you know if it's entering? By the arrow direction. Current entering the node is equal to the current leaving the node. And so we have an equation for this. If I call this current I1, and I call this one I2, and I call this one IT, I can write this in an equation. That equation says that IT is equal to what? IT will be equal to I1 plus I2. Again, I1 and I2, they are leaving the node. And this one is leaving the node. And of course, in this case, what is leaving the node is IT. And so I1 plus I2 will give us IT. Yes, and of course, now you can do some subtraction that if you have I1 and IT, you can say that IT minus I1 will give you I2. So this is the equation. It's called Kirchhoff's current law. So the same rule applies here. If you wanted to know, okay, what is the total power draw for the circuit? The total power draw is going to be the power for each individual load, and you just add them together. So PT for the parallel circuit is going to be PT is going to be equal to P1 plus P2, right, for the parallel circuit. Secondly, the next thing we need to discuss is the resistance. How do we find the resistance for a parallel circuit? Okay, so for the series circuit, we said we just add the resistors and we are going to get the resistances, but it's not the same for the parallel circuit. Instead, what we do add, we're going to add the conductance for each load, and then we will find the total conductance, and then we can find the total resistance. So RT for the parallel circuit, right? RT is going to be equal to the sum of the conductances. Now conductance, I call it GT. So how do you find GT? Again, conductance is 1 over resistance. So again, GT is going to be equal to what? 1 over R1 plus 1 over R2. So again, you find the total conductance in the parallel circuit, and then you convert the conductance to resistance by saying resistance is going to be 1 over conductance. All right. So this is how you find the total resistance in a parallel circuit. And why is that the case? Okay, the reason it is the case is because in the parallel circuit, every time you add one more load, the resistance actually lowers, right? And why does it lower? Because you're actually drawing more current. And this is why. Let me give you an example. Say if you have, let's say we have a circuit here with one load. Let's say we have a 10 volt supply, and we have a 10 ohm resistor, right? We can ask our question, what is the current coming out here? So what is the current going through this resistor? What is the current? The current is going to be, what is the voltage across it? So we use Ohm's law. And Ohm's law says that I is equal to V over R. In this case here, what is the voltage across the resistor? So I'll put VR. The voltage is 10 volts, right? So it's going to be equal to 10 over 10. So our current is 1 ampere. Do you guys agree? So our current is 1 ampere based on Ohm's law. Again, this is Ohm's law here. Now, what happens when you add another load to it? And again, we're explaining why our resistance is not straightforward. In other words, the total resistance of the circuit is not straightforward. For the series circuit, we said it's straightforward. Resistance is going to be R1 plus R2, but for the parallel circuit, it's not straightforward. And we're explaining why. So again, if we have one resistor, straightforward, we have 1 ampere of current flowing through this resistor. What if we add another resistor? Say we add another 10 ohm resistor, Okay. Now we said the current for each, the current flowing is determined only based on the resistance of that resistor and the supply. Since 10 volts is across this, we can also calculate the current that's going to be flowing in this branch. The current is going to be I is equal to VR over R. So that's going to be 10 volts because it's in parallel, 10 volts over 10 ohms. So we have a current flowing in this branch of 1 ampere as well. Yes? So now if we ask the question, what is the total resistance of the circuit? Here, when we had one resistor, the total resistance was 10 ohms. Now that we have two resistors in parallel, the total resistance is not 10 ohms anymore, but the total resistance we will see has lessened. So how can we find the total resistance? There are different ways we can find it. Let's do the first way first. The first one is we can actually find the total current and divide the total current by the voltage, and we can find the resistance that way. So if we ask the question, well, what is IT? What is IT? Based on what we talked about with Kirchhoff's current law, we see that we have two loads. Each of them are drawing 1 ampere. So of course, the total current coming in needs to be the total current here. So we can say that IT is equal to I1 plus I2, which is going to be equal to 1 ampere plus 1 ampere, which is equal to 2 amperes. So we can say, based on the two loads that we have, the total current that is coming from our source, our battery, is actually 2 amperes, because 1 ampere will pass here, 1 ampere will pass here, they add up together to form 2, right? So after we find IT, we can use Ohm's law. Now Ohm's law says that R is equal to Vs over IT. So this is the first way we can find the resistance. We find the total current first, and then we use Ohm's law, where we divide the voltage by the current to find the resistance. And so we have here 10 volts divided by 2 amperes, and it gives us 5 ohms, right? So this is the first way we can find the resistance. We can find the current, and then we can use Ohm's law, and then we can find, okay, what is the total resistance of the circuit? And notice here that even though we have two 10 ohm resistors, the battery or the voltage source is saying that, hey, I'm supplying 2 amperes here, so the resistance must be lower. And so the resistance that the battery is seeing is actually 5 ohms instead of 10 ohms. If it was just one resistor, it would be seeing 10 ohms, so it was supplying 1 ampere. Because remember, the battery voltage does not change, right? The battery voltage does not change. Now the current changes. And so when the current changes, we need to evaluate what is the total resistance that the battery is seeing based on this new current. And so the battery is seeing 5 ohms, even though there are two 10 ohms there connected in parallel. This is what the battery is experiencing. So this is the first way to find IT. I'll put a box around it. So there's the first way to find IT. To find RT, or the total resistance. What is the second way to find RT? The second way to find the total resistance is the method that we just described. We're going to find the total conductance, and then we're going to take 1 over it and find our resistance. So in this case here, GT is going to be equal to 1 over 10 ohms plus 1 over 10 ohms, which gives us 2 over 10 ohms, right? Okay, what is 2 over 10? It's the same thing as 1 over 5. So let's keep going. So 2 over 10 is equal to 1 over 5. 1 over 5 ohms is the same thing as what? 0.2, correct? So GT is equal to 0.2 ohms, right? Now to find RT is going to be equal to 1 over 0.2 ohms. And that gives us, okay, sorry, our unit here should not be ohms, so I'll just remove it. Let me just move the unit. We have a different unit, and that unit is Siemens. So I'll put S here. So the unit for conductance is Siemens. So again, after we find GT, we take 1 over GT. So 1 over 0.5, 0.2 gives us 5. And so now our unit is going to be 5 ohms. So this is the second way to find the resistance. You find the total conductance, and we take 1 over the total conductance, and now we find the resistance. Now there is a third method that we can use, and this method is used. Okay, let me just make sure we are recording. All right, great. So again, we have a third method that we can use, and the third method is only used when we have 2 resistors, right? So we can only do 2 resistors at a time with this third method, and this third method says that RT for parallel is going to be equal to R1 times R2 over R1 plus R2. And again, we can only use this for 2 resistors. Okay, so let's apply this in our case here. What is our R1? We're going to have 10 ohms times 10 ohms over 10 ohms plus 10 ohms. And that gives us 100 ohms. So you can see we have the unit, now we have 2 ohms, right? Divided by 20 ohms. And so the unit will cancel out. And so what 100 over 20 gives us 5. So our answer is equal to 5 ohms. All right, so this is the third way you can find RT in a parallel circuit. All right, any questions before we look at some examples? Any questions? Okay, if no questions, let's look at an example with the parallel circuit, an example with the series circuit, right? And again, all the rules that we talked about, we are going to apply them. So here's the example that I have for you. Make sure you have your calculator, and so you can work this together with me. So let's say series circuit example. All right, so first we're going to draw the circuit. And I'm going to use 3 resistors. So we have R1 here, R2, R3, Vs. Let's go with 25 volts, and let's go with 100 ohms. Let's go also with 1 k ohms and maybe 470 ohms. Okay, 470 ohms. All right, so there's another technique I will show you. It's called voltage divider equation. So we'll apply it here as well. And so you're given a circuit like this with 3 loads, and you are told find the following. Now, of course, we're going to be using the problem-solving method. Find RT, total resistance. Find then IT, total current. Find also PT, the total power for the circuit. Find the power rating of this resistance, PR1, so PR1, and then find PR2, and then also find VR1, then find VR2, then find VR3. Okay, I think this is enough. So you're told to find these things, right? Okay, let's do the problem-solving method. What are we given? We need to write what we are given. Okay, we are given that R1 is equal to 100 ohms. R2 is equal to 1 k ohms. And R3 is equal to 470 ohms. Vs is equal to 25 volts. What do we know? Okay, what are we told to find is right there. I'm not going to write it again. What do we know? So this is where we write our equations that we know. Now, how do you know these equations? Okay, I just gave them to you, right? They are right here. You should have them written down, right? About the series. You should have a page with series circuits and all the equations that you can use. So as you continue to use it, it will be more familiar to you. So what do we know? Well, we can know the first one we're going to highlight is RT, right? Because we know that RT is the sum of all the resistors. So let's start with this one. So in our solution here, we can say that RT is going to be equal to R1 plus R2 plus R3. What else do we know? We can then find IT, correct? IT is going to be equal to Vs over IT, and that is Ohm's law, right? Vs over IT. Again, just to write Ohm's law. Ohm's law says that V is equal to I times R. And of course, you can change it around. I is equal to V over R. R is equal to V over I. Now you can apply this to the whole circuit where you do IT, or you can apply it to an individual component where you do VR1 over R1, right? Let's continue. What else do we know? What else do we want to find? Well, we also know that that all the voltage drops is going to equal to Vs. So we can say that Vs is going to be equal to VR1 plus VR2 plus VR3. Now, how do we find the individual voltage across here? Well, there are two ways we can do it. For example, I will give you an equation. We can, if you wanted to find VR1, we can say that VR1 is going to be equal to the current, which is IT, because we said in series circuit we only have one current, so we only use IT. IT current times, what is V? V is equal to the current times the resistance. So again, you can see we apply Ohm's law to the individual resistor. So to this resistor is going to be the voltage across it is going to be the current going through it times the resistance times R1. So this is one way you can find the individual voltage across the components. The second way you can find it is by using the voltage divider method. So I'm going to use this to find VR3. VR3, again, this is the voltage divider method. This is where you take the fraction of that resistor. It's going to be R3 over the total resistance, RT. And so again, it's the ratio of R3 over the total resistance times your supply voltage, which is Vs, right? This is called the voltage divider method. Okay. Again, what is PR1 and PR2? I just put one for PR1. PR1 is going to be equal to P1 times 1.2. And how do we find P1? So let's find PT. So PT, power is equal to voltage times current, right? Voltage times current, that's what we discussed. That's for power. Now, how do you find the power in resistor 1? P1, you can say P1 is equal to VR1, yeah? VR1 times the current, because it's the same current going through it. So that's one way you can find the power. Or you can say that P1, or you can say P1, well, I'll use it for P2. So this is another way you can find power. P2 is going to be equal to VR2 squared over R2. Again, you see that we have different ways we can find power. We have different ways we can find the voltage as well. So again, it's up to us to identify which equations we can use for series. So again, this sheet is very helpful. We start with this one. We know this. Once we know this, we can then proceed. Let's go ahead and solve this, and then we'll do an example for parallel. So this step is very important, writing the equations that relate your input to your output before you start with your solution. So I'll start the solution down here. All right, so for my solution, what is RT? RT is going to be equal to R1 plus R2 plus R3, which equals to 100 plus 1K plus 470 Now keep in mind a K is 1,000, so this gives me what? 1,570 ohms. Or I can say it's the same thing as 1.57 K ohms. All right. The next step, so this is my final resistance. I can then find my total current, IT, is going to be equal to VS over RT. Sorry, this should be RT, sorry. So voltage over resistance, according to Ohm's law. And that gives me 25 volts over 1.57 K. I'm just going to write it out, 1570 ohms. Now, this is where it's important for me to it's very important for me to have enough significant figures in my answer so that I don't have errors later on. So again, here it's going to be 25 divided by 1570. And that gives me, if I write it, 0.01592, which is the same as, that's amperes, which is the same as 15.92 milliamps. All right. Okay. The next step, so I have already found this. If you look here, we have found this, correct? We have found this. We can then find the total power. What is the total power? Now again, we can find the total power using this equation right here. That power is equal to voltage times current. Or we can use the equation for voltage and resistance and find the power as well. So I'll use that one, power, because it's if I use this equation, it's more accurate because we don't have any decimal places. Power is going to be equal to Vs squared over RT. And that gives me 25 times 25 over 1570. And it gives me 0.39808 watts, or I can write it as 398.08 milliwatts. The next step is to, so we find total power. We need to find power for, before we find the power rating for 1 and 2, let's find this voltages here. So for VR1, we can go ahead and use this method here where we have IT times R1. Like I said, we can go ahead and definitely use that. Another way, we said we can use the voltage divider method. So I'll just put that, this is the voltage divider method. It's going to be more accurate because we don't have to use the current. Notice the current has a lot of decimal places. We only use a few. So our answer is less accurate. So, and I can show you that. Let's go ahead and use the voltage divider method to calculate VR1. All right, so VR1 is going to be R1 over RT times Vs, which gives us 100 over 1570 times 25. So we have 1.592 volts. Then we can also calculate VR2. Now I'm going to use a different method to calculate VR2. I'm going to use this method right here to calculate VR2. VR2 is current times R2, right? IT times R2, which is going to give us, and our current is 15.92 milliamps, 0.01592 amperes times 1000. And that gives us 0.01592 times 1000, that gives us 15.92 volts. And then VR3, I can choose any of these methods to calculate VR3, or I can use Kirchhoff's voltage law. Now, with Kirchhoff's voltage law, we know that Vs is equal to VR1 plus VR2. So if we know Vs and we know VR1 and VR2, we can calculate. So again, we're saying the voltage here and here and here adds up to this one. Since we already calculated the voltage here and the voltage there, we can simply subtract from this one to find this one. So VR3 is going to be Vs minus VR1 plus VR2. And that will give us 25 minus 1.592 minus 15.92, which gives us 7.488 volts. All right, and then we can, since we know the voltages now, we can simply calculate the power here. Again, power is going to be, for individual power, is going to be voltage times current, or V squared over R2. Now, in this case here, we can calculate the power and multiply it by 1.2 in the same line, so we can find PR1 and PR2. So PR1 is going to be, we'll find the power first. It's going to be VR1. VR1 squared over R1. So that's how we find the power. And then we multiply it by 1.2. And we have our answer here. And the same thing for PR2. So you can see that there are multiple ways to calculate voltage and current and power. As long as you have your accurate answers, that's what's important. You will not be asked to use any particular method. So in this case here, it's going to be, oh, I'm sorry, I was blocking you. Okay, so if we calculate PR1, we're going to have VR1 is, what is VR1? 1.592 times 1.592 divided by R1, and R1 is 100, and then times 1.2. That gives us 0.03041 watts, or 30.41 milliwatts. Likewise, if we do R2, VR2 is 15.92 volts times 15.92 divided by the resistance of 1K, 1000, times 1.2. So we have 0.3041 watts, which is the same as 304.1 milliwatts, right? So we have completed everything that was asked of us in the problem. We got this one, this one, this one, this one. So again, where can you have errors in your, you need to have enough significant figures, especially when you calculate current. And if you use current to calculate other things, you're going to have these errors as well. That is why here, when I calculated VR1, I did not use the current, but I used the voltage divider method. Here I used the current, but it was pretty straightforward. And here I did not use the current too, I just used V squared over R. So this is the series example. I will share with you a parallel example as well. So just to let you know, before I go ahead and share the parallel example, this seems like a lot. It seems like, hey, there's a lot to know, a lot to remember, but it comes with practice. If you will practice it a couple of times, you get to understand it better. You get to understand why we are using the different equations for series and why we're using some different ones for parallel. And you get to see, so with Ohm's law, you can see that we use Ohm's law for the entire circuit, yeah? And we can use Ohm's law for the individual components as well. So you can see we can use the voltage for the resistor, the current through the resistor, and we can get the resistance of that resistor and so forth. And we go vice versa or backwards and forwards. Let me share one example for parallel, and then we'll end. So hopefully sometime next week, we're going to have maybe a session where we can work some problems, and we can just, go through your assignments as well, to ensure that you can get some practice that you need. Because like I say, it's not intimidating. There is some information that you need to know on each of them. But with that information, you also need to practice. So there is a presentation 4 and presentation 5 that you should go through as well. They have some pictorials to help you. There are also some examples that you can try as well. Okay, so this is the series 1. I'll try to upload this copy on Canvas as well. Let's look at the other example, which is a parallel example. And then that will be it. All right, so in this circuit, we have a parallel circuit, right? Parallel. So let's start with a source. Let's go with 25 volts. And let's have, so last time we had 3 loads. We can have 3 loads in this one too. Maybe 2 loads is fine. So we have our R1 here and our R2. So let's say that R1 is going to be equal to 10 ohms. And let's say that R2 is going to be equal to 100 ohms. So obviously, based on Ohm's law, which of these components are going to have the highest current? Notice that the voltage is the same, right? And this one has a smaller resistance, this one has a greater resistance. Which of these is going to have the higher current? What do you think? Remember, resistance is the opposition to the flow of current. So the more resistance you have, the less current is going to flow through you. Especially, again, both of them are connected to 25 volts. The smaller resistor will have the highest current flowing through it, right? So first thing we want to do, given a circuit, we are told to find IT, find RT, find I1 and I2, find PT1, PT, total power, find PR1 and PR2. That's the power rating for the 2 resistors. All right? Okay, first step is to find the current. Now we use Ohm's law on that individual resistor, right? So again here, what do we know? Let's write our equations first. What do we know? We know that the current in each branch is based on the resistance. So we can say that I1, let's call this I1, and I2. The current is going to be equal to the voltage VR1. Now again, VR1 is the same as the battery voltage. So here we don't have to say VR1 or VR2, we can just say V, right? So VR1 over R1, that's Ohm's law for us. And that gives us I1, and we can say I2 the same thing, right? VR2 over R2. That will give us our current here. Now, based on the Kirchhoff's current law, KCL, we know that our IT is coming from our battery. It's going to split up here. Some will go here, and some will go there. So we know that IT is equal to I1 plus I2. So we have already found our total current. And with that total current, we can find RT. But we're going to use just two methods to find RT. So again, we can say that RT, this is Ohm's law, is equal to Vs over IT. So we can find our RT like that, or we can say that RT is equal to 1 over GT, where GT, we know that GT is going to be equal to 1 over R1 plus 1 over R2. So there are these are the two ways we can find the resistance, right? How do we find the total power? Of course, PT is going to be equal to, we can say that PT is V squared, is V times I, Vs times IT. That will give us our PT. Another way we can calculate PT, like we said, we can say that PT is going to be equal to, we can find the power for the individual components and we can add them up. Let's find P1. So for P, let's find P1. P1 is going to be equal to Vs times I1. So the power in the resistor is going to be the voltage across it times the current flowing through it. That's one way to find P1. The other way to find P1 is given the voltage across it on the resistor, we can say that P2 is going to be Vs squared. That's another way we can find power over R2. So we can use the voltage squared over the resistance, or we can use the voltage times the current to find power. Now, of course, to find the power rating, we simply need to multiply this by 1.2, right? So PR1 is equal to P1 times 1.2, and PR2 is equal to P2 times 1.2. All right, and that's it. So let's go ahead and write our solution now. So we have our given. What are we given? Vs is equal to 25 volts. R1 is equal to 10 ohms. R2 is equal to 100 ohms. So this is what we are given. This is what we're told to find. This is what we know. Now we have our solution. Okay, so again, we're going to find, we said we'll find I1 and I2 first. So again, we have I1 is going to be equal to Vs, which is the same as VR1, which is the same as VR2, over R1, which gives us 25 over 10. And that gives us 2.5, right? So I1 is 2.5 amperes. What about I2? I2 is going to be equal to Vs over R2, which is 25 over 100, which gives us 0.25 amperes, right? So you take a 25, you bring it back 1, 2, right? So this is 2.5 amperes. So this is our answer so far. So what is our total current coming from our battery? IT is going to be equal to I1 plus I2, which is equal to 22.5 plus 0.25, which gives us 2.75 amperes. And we can find our total resistance using that. Let's leave the total resistance for now and let's solve this power stuff, right? So for P1, we can use this method and then we'll just multiply by 1.2 to find PR1. So PR1 is going to be equal to P1, which is Vs times I1, and we'll just multiply by 1.2, which is 25 by 2.5 by 1.2. That gives us, let's see what our calculator says. $25 times 2.5 times 1.2. So this is 75 watts. 75 watts. Likewise, for PR2, let's use this method here where we do V squared over R2. It's going to be V squared, Vs squared over R2 times 1.2, which is 25 times 25 times 1.2. Of course, we will divide this by R2, which is 100. So on my calculator here, I see 25 times 25 divided by 100 times 1.2. And this gives me 7.5 watts. So the total power in the circuit, PT, is going to be P1 plus P2. Now I did not calculate them, so I'll just put them together. So P1 plus P2, right? Another way I can calculate the total power is simply by multiplying the voltage times the current. It's also equal to Vs times IT, which gives me 25 volts times 2.75 amps. 25 times 2.75. Okay, hold on. Let's see if we have a problem somewhere. Yep, that's fine. So it's going to be 68.75. So notice here, this is the power rating. This is the power times 1.2. This is the power times 1.2. This is just the power, right? If I got the power rating, if I multiply this by 1.2, I will get this plus this. Okay, is there anything else we have left to calculate? We get this. We're missing the resistance, right? So again, two ways to find the resistance, RT. You can find RT by saying that it's going to be Vs over IT, which is going to be 25 volts over 2.75 amps, which gives us, and this is our last problem, 25 divided by 2.75 gives us 9.090 amperes. That's ohms. The other way is using the conductance method. And so for that method, we first find the total conductance, where we say that GT is going to be equal to 1 over 10 plus 1 over 100, which gives us 0. 1 over 10 is 0.1, 1 over 100 is 0.01, so we have 0.11. And then RT is going to be 1 over GT, which is 1 over 0.11, which gives us, calculator please, one divided by 0.11 gives us 9.090 ohms. And the third method I mentioned to you is only when we have two resistors, we say that RT is going to be equal to R1 times R2 over R1 plus R2. And so here we're going to have 10 times 100 over 110. Right? So what is 10 times 100? It's 1,000, right? $1,000 divided by 110 gives the same thing here, 9.090 ohms. Right? So this is where we have come to the end of the class. Like I said, there are some equations that govern series and parallel. We need to know the difference. We need to have a sheet for series, right? That when we practice the series circuits, we use these equations over and over so we can recognize them and we can choose the right ones. And then for parallel, we need to know, okay, these are the equations that govern parallel. And so when we work the problems over and over, we become familiar with it. Because in the exam, when you have a formula sheet, you need to know how to select the correct formulas. Any questions before I stop here? So I would invite you to go ahead and just review the material. Just take some time, go through the presentations, 4 and 5. Probably do that before you do your work or if you submit your midterm exam as well. You guys have a great weekend.
What class is this? Number 5?
Pardon?
I said, what class session is this?
What class is this?
Yeah, class session. What number?
Oh, this is number 4.
Okay.
Okay.